Last time we discussed how our humble int list could be transformed into a more powerful data structure called an S list. And along the way, we had many different improvements we gave our data structure. Now, I think it's not a bad idea to know about each of these improvements, what they were, what good they did, and not from the perspective of, I'm not going to ask you on an exam like, what were the 5 improvements to turn N list into S list? That's useless, right? Whatever. There are many different improvements one could make. Our particular set's not important. What is important is thinking about the different kinds of improvements we made. So for example, improvement number 2, we took our int list and we put this layer of abstraction between us and the naked data structure. And in that way, we hid the entire notion of references for people that wanted to have a list, right? That way, the user doesn't have to think about references. It's easier to use. And then there's a neat side effect that we could have a 0-size list. It just kind of came for free. But then there are other kinds of improvements where one example is we added a size variable, which made size faster, right? So in that case, that's a totally different kind of change. It was about optimizing its speed. Another example would be when we added our Sentinel node. So that optimization didn't affect speed or usability. That affected our ability to look at the code and ensure, 1, that it's correct, and 2, to make it easier to build more functionality on top. So it made it easier for the developer of the data structure. So easier for the user, faster, easier for the developer. And then here we have another example of easier for the developer, where I said it's not a bad idea to have helper methods to make your code nice. Okay? So keep that in mind as you move forward and you're working on data structures. There's many different ways in which you can make things better. So we're going to talk about one such improvement we can make to our S lists and bring them into the world of so-called D lists, as they will be called in our notes. So to motivate this, I'm going to make the observation that S lists, while they're so much better than int lists, they still have some flaws. One of them is that operations which involve the back of the list are going to be slow. So if we want to insert something at the back, we have to step through the list, like do, and then finally reach the back. Okay, so that's not ideal, and so we're going to try and fix that. So what I want to do is, rather than give it away, right, I think it's good practice for you to think about what could maybe make this better. So I recommend you pause the video, but actually even better is maybe you watch these videos with someone you know, and it would be super cool if you're right next to each other. Now you can argue about it and discuss, how could we change this data structure? What even, like, the whole, anything is within the realm of possibility. And you just got to pick the thing. So the insert back is also fast. Okay. All right, so I'm assuming you've paused. So one solution is to add a back pointer, right? Adding a back pointer does the following. I want to insert back. Well, that means I need to change size to 4, and that means I need to take this pointer and look at this tail, which is currently null, and redirect it so it points at a new node, and then set the back pointer. So that actually should be pretty easy. Okay, well, what about getting the back item or deleting the back item? Will those be fast? And again, this is a great time for you to argue with someone you know and try and decide if these things will be fast or not. And maybe the answer is, yeah, that's fine. Maybe all we need to do is add a back pointer, and then this thing can handle insertion, getting, or deletion perfectly fine. Okay. All right, so now that presumably you've thought about it, I will reveal the secret that, in fact, it is not enough. Having a .back pointer here is not enough. In fact, it's going to make it, so while get and insert will be plenty fast, delete will not be fast, because if you wanted to delete, well, you might think it's easy, right? If I want to delete this item, I just follow this arrow and then delete, cross it out. But then you have to think about, what is deleting actually, right? We haven't talked about delete operations, so that's part of why this problem was a challenging one. So deleting, obviously, we'd have to change the size to 2, but then the other things we'd need to do are, 1, set the back pointer to this node, and then we'd have to null that out. So in other words, the deletion operation involves nulling this, changing this to 2, and setting the back pointer here. Now the difficulty is that with a back pointer, we don't know who has second to back. So if we wanted to actually, say, set this thing to null, or set the back pointer, we're going to have to walk through the whole list and find, somehow, the second to last item. So maybe we would write a private method called get second to last. Now you might think, okay, well then I'll just add a second to back pointer. But then the problem is now you need a third to back pointer to keep the second to back pointer up to date. So we need something else. So next design challenge for you. And I hope you'll treat this as like a fun challenge and not just watch all the way through. And whenever you get to project 1, you're going to be thinking about these things, and you'll probably want to be diagramming things out. Okay, so think about this. What else could we change about this? Any change to the topology of this list is fine with me. Don't worry too much about, I don't know, implementation and how difficult it might be. Okay, so the standard solution is to add previous pointers. Okay, so what you can do is every single node is going to have a backwards pointer at whichever node came before it in the list, and hence the term that we've heard, doubly linked list. So over here we still have our Sentinel, its previous pointer is just null, and then we have a bunch of items over here. So now when we want to delete, well, in that case, we know who the second to last is. So we just need to set back to here. We need to set this to null, and that's it, actually. Then we're done. Okay. You do not actually need to set this to null because, well, we'll learn about garbage collection later. But really, all you need to do is get rid of this and get rid of this. Or sorry, get rid of this and point this. All you need to do is set next to null and set the back pointer to this node. Okay, that's what deletion would mean, other than also changing size. Okay. Now, the great thing about having these forward and backwards pointer is that now all operations can be fast. Insert, get, delete, front, and back. All of that can be speedy. Okay? And that will be very important to you when you do project 1. So I'm not going to do the code, as I mentioned earlier, because this is going to be a big piece of that project. Okay? So here's a non-obvious fact that I want to warn you about before you start working on the project. This approach, as we have it, has an annoying special case here, which is that sometimes the back pointer is pointing at the Sentinel, and sometimes the back pointer is pointing at a so-called real node. Okay? And so when you work on project 1, you might run into this issue. And so I'm going to outline a couple of approaches you might consider using for project 1. So one of those solutions is to have 2 Sentinel nodes, a front Sentinel, sentf, and a back Sentinel, sentb. Now at this point, this is something that probably isn't super obvious unless you really sit down with it and draw out some diagrams and get to understand like why it might be tricky. It might even be all the way to the point that you're programming that you can, like, it might be that you're trying to code up the front Sentinel only solution when you run into the trickiness. But suffice it to say, I want you to be aware that having 2 Sentinels is not a bad idea. But in fact, an even better idea is to have a so-called circular list or a circular Sentinel. So in this approach, an empty D list, right, will have size 0, a Sentinel node that points at itself, its previous is itself, and its next is itself. If you have a size 2 node, for example, well, in this case, the Sentinel link will point to the Sentinel, and then from there we can keep going forward, and eventually we loop back around. Okay? So that's my preferred topology for project 1. Okay? So that's basically the big picture of D lists, and you'll get to really appreciate it whenever you try and implement it. Okay? So just to summarize what would be our improvement number 7, while it is fast to have a data structure with back and previous nodes, there's going to end up being a bunch of special cases that are super annoying, right? The fundamental issue was that the back node sometimes points at a Sentinel and sometimes at a real node. But what you'll find is there's a bunch of if statements. It's going to be ugly. So I'm going to suggest, again, on project 1, either maybe have a pair of Sentinels or have this circular topology. Okay. So then just to summarize all the things we did, bringing ourselves all the way to S lists. These were good for everything but delete back. And then we added these 2 additional improvements, this one for speed and this one for coding simplicity. And yet there's still many things we could do to make it even better. Because right now our data structure doesn't handle, for example, doing things like getting arbitrary items in the middle. It doesn't allow us to deal with weird exceptions, like people trying to add nulls to the list. What if something goes wrong, right? How do we handle things more gracefully? And those are things we'll be discussing over the coming weeks.